Hi, this is Sir Christian and welcome to my video lesson. Again, this is Sir Christian, and for today's lesson, our topic is circular motion. To give you an idea of the things that we'll be discussing in this video, we will start in discussing what circular motion is, period, centripetal acceleration, Newton's second law, and centripetal forces. So get your notebooks and ready to learn. A child riding on a carousel, you riding on a Ferris wheel, both are examples of uniform circular motion. When the carousel or Ferris wheel reaches a constant rate of rotation, the rider moves in a circle at a constant speed. In physics, this is called uniform circular motion. Developing an understanding of uniform circular motion requires you to recall the distinction between speed and velocity. Speed is the magnitude, or how fast an object moves, while velocity includes both magnitude and direction. For example, consider the car in the graphic on the screen. Even as it moves around a curve at a constant speed, its velocity constantly changes as its direction changes. A change in velocity is called acceleration, and the acceleration of a car due to its change in direction as it moves around a curve is called centripetal acceleration. Although the car moves at a constant speed as it moves around the curve, it is accelerating. This is a case where the everyday use of a word, acceleration, and its use in physics differ. A non-physicist would likely say, if a car moves around a curve at a constant speed, it is not accelerating. But a physicist would say, it most certainly is accelerating because its direction is changing. He could even point out, as we will discuss later, that a net external force is being applied on the car, so the car must be accelerating. Uniform circular motion begins the study of rotational motion. As with linear motion, you begin with concepts such as velocity and acceleration, and then move on to topics such as energy and momentum. As you progress, you will discover that much of what you have learned about these topics in earlier lessons will apply to circular motion. In the simulation showed on the screen, the object moves around the circle at a constant speed. The blue velocity vector represents the direction and magnitude of the object's instantaneous velocity. And now note how it changes as it travels around the circle. And now, let's move on to the uniform circular motion. The toy plane on the screen moves in a uniform circular motion as it is held by this person. The identical length of the velocity vectors in the diagram indicate a constant magnitude of velocity, a constant speed. When an object is moving in uniform circular motion, its speed is uniform or constant and its path is circular. The plane does not have constant velocity. In fact, its velocity is constantly changing. Why? As you can see in this diagram, the direction of the velocity vector changes as the plane moves around the circle. A change in the direction of velocity means a change in velocity. The velocity vector is tangent to the circle at very instant because the plane's displacement is tangent to the circle during the very small interval of the time. So again, an object moving in a uniform circular motion has a constant speed, but its velocity is constantly changing due to the change in its direction, and the velocity vector is tangent to the circle. In math, tangent means a straight line that touches a curve. Uniform circular motion is important in physics. For instance, satellite in a circular orbit around the Earth moves in a uniform circular motion. Period refers to the amount of time it takes for an object to return to the same position. The concept of period is useful in analyzing motion that repeats itself. Let's use the example on the screen to illustrate period. The object moves around the circle at a constant rate, which is to say, in uniform circular motion. It returns to the same position on the circle after equal intervals of time. The period measures how long it takes the objects to complete one revolution. In this example, it takes the object 5 seconds to make a complete lap to make around the circle. When an object is in uniform circular motion, that motion is often described in terms of the period. Many other types of motion can be discussed using the notion of period. For example, the Earth follows an elliptical path as it moves around the Sun, and its period is called a year. A metronome is designed to have a constant that provides musicians with a source of rhythm. This equation enables you to calculate the period of an object moving in a uniform circular motion. The period is the circumference of the circle, 2 pi r, divided by the object's speed. To put it more simply, it is distance divided by speed. Let's say, for example, the circle wherein the object is moving has a radius of 0.50 meters and has a velocity of 2.0 meters per second. What is the speed of the object? So if we are to solve it, period is equals to 2 pi r divided by the object's speed. Then we substitute 2 times 3.14 times 0.50 meters divided by 2.0 meters per second. And this will now give us the period of the object, which is equals to 1.6 seconds. This means that the time it takes for the object to return to its original position is 1.6 seconds. Centripetal acceleration refers to the centrally directed acceleration of an object due to its circular motion. An object moving in uniform circular motion constantly accelerates because its direction and therefore its velocity constantly changes. This type of acceleration is called centripetal acceleration. On the screen is a vector analysis of centripetal acceleration that uses a satellite as an example of an object moving along a circular path. As the diagrams indicate, the satellite's velocity is tangent to the circle. In uniform circular motion, the acceleration vector always points toward the center of the circle, perpendicular to the velocity vector. In other words, the object accelerates towards the center. This can be proven by considering the change in the velocity vector over a short period of time and using a geometric argument, which we will not dwell with in this video. Centripetal acceleration is expressed in this equation. The magnitude of centripetal acceleration equals the speed squared divided by the radius. Since both the speed and the radius are constant in uniform circular motion, the magnitude of the centripetal acceleration is also constant. It is also useful to express centripetal acceleration in terms of angular velocity. Substituting velocity as equals to the product of radius and angular velocity into the first expression, we find centripetal acceleration equals the square of the product of radius and angular velocity divided by radius, or to simplify it, centripetal acceleration is equals to the product of radius and square of angular velocity. So, we can express the magnitude of centripetal acceleration using either of two equations. With uniform circular motion, the only acceleration is centripetal acceleration. But for circular motion in general, There may be both centripetal acceleration, which changes the object's direction, and acceleration in the direction of the object's motion, or tangential acceleration, which changes its speed. If you ride on a Ferris wheel, which is starting up, rotating faster and faster, you are experiencing both centripetal and tangential acceleration. For now, we focus on uniform circular motion and centripetal acceleration, leaving tangential acceleration as another topic. For you to better understand centripetal acceleration, let's try to answer the following problems. Example number 1. What is the magnitude of the centripetal acceleration of a car following a curve with a radius of 500 meters at a speed of 25 meters per second? In this problem, we are already given of the radius and our speed. The radius is equals to 500 meters, while the velocity or speed is equals to 25 meters per second. Then, we are required to find out the magnitude of the centripetal acceleration. Since we are already given of our velocity or speed and radius, it's just appropriate that we use our first formula, which is centripetal acceleration is equals to the square of our speed or velocity divided by radius. We then substitute. We get the square of our velocity divided by 500 meters. We then simplify by getting the square of 25 meters per second, which is equals to 625 meters squared per second squared. Then we divide it by 500 meters or our radius. Then it will give us our centripetal acceleration, which is equals to 1.25 meters per second squared. Example number 2. You twirl a lasso over your head at a constant angular speed of 3.8 radians per second. What is the centripetal acceleration in meters per second squared of the lasso's tip? 1.4 meters from your hand. So in this problem, we are already given of our radius and our angular velocity. Our radius is equals to 1.4 meters, while our angular velocity is equals to 3.8 radians per second. Then, we are required to find out the magnitude of our centripetal acceleration. In this problem, we are already given of the radius and the angular velocity. So, it's just appropriate that we use our second formula, which is centripetal acceleration is equals to the product of our radius and the square of our angular velocity. We then use our formula by substituting. Our radius is equals to 1.4 meters. Then we multiply it to the square of our angular velocity, which is 3.8 radians per second. We then simplify it first by getting the square of our angular velocity, which is equals to 14 radians per second squared. We then multiply it to 1.4 meters or our radius. Then, it will give us our centripetal acceleration, which is equals to 20 meters per second squared. Newton's second law and centripetal forces. If you hold onto the string of a yo-yo and twirl it in a circle overhead, as illustrated in the graphic, you know you must hold the string firmly or the yo-yo will fly away from you. This is true even when the toy moves at a constant speed. A force must be applied to keep the yo-yo moving in a circle. A force is required because the yo-yo is accelerating. Its change in direction means its velocity is changing. Using Newton's second law, which is force equals to mass times acceleration, we can calculate the amount of force as the product of the object's mass and its centripetal acceleration by substituting the centripetal acceleration formula to the expression. So, the expression will be force equals to mass times the square of speed divided by the radius. This applies to any object moving in uniform circular motion. The force, called a centripetal force, points in the same direction as the acceleration, towards the center of the circle. The term centripetal describes any force that causes circular motion. A centripetal force is not a new type of force. It can be the force of tension exerted by a string, as in the yo-yo for example. Or it can be the force of friction, such as when a car goes around a curve on a level road. It can also be a normal force. For example, the walls of clothes dryer supply a normal force that keeps the clothes moving in a circle, while the holes in those walls allow water to spin out of the fabric. Or, as in the case of a motorcycle rider, the centripetal force can be a combination of forces, such as the normal force from the wall and the force of friction. Sometimes, the source of a centripetal force is easily seen, as with the string or the walls of a dryer. Sometimes, that force is invisible. The force of gravity cannot be directly seen, but it keeps the Earth in its orbit around the Sun. The centripetal force can also be quite subtle, such as when an airplane tilts or banks. The air passing over the plane's angled wings creates a force inward. In each of these examples, a force causes the object to accelerate toward the center of its circular path. Identifying the force or forces that create the centripetal acceleration is a key step in solving many problems involving circular motion. And now, let's try to solve problems involving centripetal forces. Example number 1. A daredevil bike rider goes around a circular track. The bike and rider together have the mass shown. What is the centripetal force on them? In this problem, we are given of its speed, radius, and the mass of the moving object. Speed is 25 meters per second, radius is 15 meters, and its mass is 180 kilograms. Then, we are tasked to solve for the centripetal force. Again, in calculating for the centripetal force, we can use Newton's second law of motion formula, which is force equals to mass times the centripetal acceleration, or speed squared divided by the radius. We then now substitute. So mass is 180 kilograms, speed 25 meters per second, and radius is 15 meters. We then simplify the equation by solving for the centripetal acceleration. Get the square of 25 meters per second, then divide by 15 meters. So that's equals to 41.6 meters per second squared. We then multiply the to the mass of 180 kilograms. So now, our centripetal force is equals to 7,500 newtons. Let's have another example. Example number 2. A 0.2 kilogram ball attached to the end of a cord is revolved in a horizontal circle with an angular speed of 5 radians per second. If cord's length is 0.6 meter, what is the centripetal force? In this problem, we are given this time of its angular velocity, radius, and the mass of the moving object. Angular velocity is 5 radians per second, radius is 0.6 meter, and its mass is 0.2 kilogram. Then, we are tasked to solve for the centripetal force. Again, in calculating for the centripetal force, we can use the Newton's second law of motion formula, which is force equals to mass times acceleration. In the first example, we substituted the first centripetal acceleration formula to the force equals mass times acceleration expression. But this time, since we are given of the angular velocity, we substitute the second centripetal acceleration formula to the force equals mass times acceleration expression. So, it will be force is equals to mass times radius times the square of the angular velocity. We then now substitute. So mass is 0.2 kilogram, radius is 0.6 meter, and angular velocity 5 radians per second. We then simplify the equation by solving for the square of the angular velocity first. So 5 radians squared is equals to 25 radians per second squared. We then multiply that to the radius of 0.6 meter and then finally to the mass of the 0.2 kilogram. So now, our centripetal force is equals to 3 newtons. Okay, so that ends our discussion. But before we officially end, let's have a summary first of the things that we have discussed in this video. Again, uniform circular motion is movement in the circle at a constant speed. But while speed is constant in this type of motion, velocity is not. Since instantaneous velocity in uniform circular motion is always tangent to the circle, its direction changes as the object's position changes. The period is the time it takes for an object in uniform circular motion to complete one revolution of the circle. Since the velocity of an object moving in uniform circular motion changes, it is accelerating. The acceleration due to its change in direction is called centripetal acceleration. For uniform circular motion, the acceleration vector has a constant magnitude and always points towards the center of the circle. Newton's second law can be applied to an object in uniform circular motion. The net force causing centripetal acceleration is called a centripetal force. Like centripetal acceleration, it is directed toward the center of the circle. A centripetal force is not a new type of force. Rather, it describes a role that is played by one or more forces in the situation. Since there must be some force that is changing the velocity of the object. For example, the force of gravity keeps the moon in a roughly circular orbit around the Earth, while the normal force of the road and the force of friction combine to keep a car in circular motion around a bank curve. So, that's the end of our video lecture. I hope you have learned something out of this video, and thank you for listening. Again, this is Sir Christian, and see you soon.